Hi, in this video we will continue on the Form 3 to Form 4 transition course. And now we are stepping into the ionic formulae, page 12. So let's get started. Now first of all, what is ionic formulae? Now ionic formulae are used to show you for an ionic compound what are the cations, what are the anions, and what are the respective numbers within a compound. It is not always one positive ion pairs with one negative ions. Sometimes we may have two positive ions, we may have two negative ions, something like that. And all of this boils down to whether or not the charges are balanced. Now, this one is very important. We say that for ionic compound, they must be electrically neutral. Okay? However, we just learned from previous video that different ions carry different charges. So if positive ions and negative ions of different magnitudes of charges come together to form an ionic compound, then the charges are not balanced. In order to balance the charge, we may need to have more than one of the two ions. For example, down here, calcium chloride is an ionic compound. It has a calcium ion. It also contains chloride ion. But knowing that for calcium ion, it is Ca2+. It obviously has a +2 charge. But on the other hand, chloride ion, Cl-, it bears a -1 charge. So if they simply group together, then +2 and -1 will give you a net +1 charge overall, isn't it? And this one doesn't work. So in order to balance the charge, we must need to have two chloride ions instead of one chloride ion. With two chloride ions, then altogether there will be two minus charges coming from the negative ions. Then the overall charge can be balanced. Okay? Now down here, if you look at the electron diagram, now you notice that for calcium chloride, the formula can be represented by two chloride ion and one calcium ion. Okay? In this way, the charges are balanced. Now, we can also express the idea using ionic formula. And here, CaCl2. This is how we describe the ionic composition of ionic compound. Now, you notice that, first of all, the number of each ion is shown by the number at the bottom right corner. Okay? So the number at the bottom right corner is showing you the number of ions. Notice that calcium, there's no number on the bottom right corner. This means that there are just one calcium ion. We don't put down Ca1, Cl2. No need. Okay? Also, you notice that there are no charges in the formula because the charges are hidden in ionic formula. In fact, we should be able to tell the charges of the ions simply by looking at the ionic formula. Okay? So bear in mind, for ionic formula, no charges. Also, the number of each ions are shown by the number on the bottom right corner. Okay? Now, so down here, this table, quite important. Basically, showing you all the combinations. Okay? Very often, we are dealing with ions with +1, +2, +3 charge, -1, -2, -3 charges. So these are simply mix and match. Now, you notice if the positive ions is having the same magnitude of charges as the negative ion, just like Na+ and Cl-, Mg2+ and O2-, Al3+ and N3-, then the formula very simple. Okay? If they start to have different charges like Mg2+ and Cl-, then we need to have two chloride ions to balance the charge. For example, this one may be complicated, Mg3N2. This one is telling you that we have 3 Mg2+ goes with 2 N3-. And you notice that the charges are balanced in this case. Okay? So all you have to know is to identify the charge of each ion. Then you make sure you find the LCM, lowest common multiple. Okay, for example, aluminium 3 plus and oxide ion, one is 3, one is 2. So the lowest common multiple will be 6. So to do that, we need to have 2 Al3 plus and 3 O2 minus, just like that. Okay. But down here, this is something you need to pay attention to. For these examples, they are all monatomic ions. So we do not have any confusion when we are writing the ionic formula. However, when we are dealing with polyatomic ions, then some problems may arise as to how we put down the formula. For example, you look at this one, ammonium carbonate. So ammonium, if you have memorized it, it should be NH4 plus. For carbonate, it should be CO3 2 minus. Okay? So to balance the charge, of course, we need to have 2 NH4 plus goes with 1 CO3 2 minus, isn't it? Now, when it comes to the formula, just now we said that, the number of ions, we can indicate it using a number in the bottom right corner. However, if you put it this way, then it is quite difficult to comprehend. People may think that, is it NH42CO3? That is not clear and ambiguous. So in order to prevent such confusion from arising, then we need to put down a bracket. We use a bracket to enclose the polyatomic ions, which may give rise to confusion. Okay, after we enclose it with a bracket, we put a 2 outside the bracket, then people know that, we have 2 ammonium ion goes with 1 carbonate ion. Okay, so this is how it works. Similar to here, aluminium sulfate. So you don't put down Al2SO4 3. Instead, you put the bracket enclosing SO4 and you put the 3 outside. Okay? Now, you may think, sir, how about I use a bracket to enclose all the ions? Then there won't be any confusion. Well, that is true, but it is wrong. Okay? In chemistry, we want to make things as simple as possible. We don't want any redundant things. So here, ammonium chloride, even though ammonium ion is a polyatomic ion, but since ammonium ion, chloride ion, they have same magnitude of charges, so NH4Cl would be suffice, would be enough. If you put the bracket here, then it will be wrong because this is not necessary. We don't have any confusion arising from this representation. Okay? Down here, similar idea. Okay? No need to add a bracket for examples that won't stir up any confusion. Okay? So this is how we put down the ionic formulae, and of course it will be your practice time. So again, 30 examples. Now here, you're doing either translating from name to formula or from formula to name. Now this one is not necessary. You can cross it out. Okay, so I will do some examples for you. For example, the first one, magnesium oxide. The first step is you need to know magnesium, Mg2+, right? You need to know it is Mg2+. Oxide is O2 minus. So you notice that they are of the same charge, isn't it? So the formula, we don't have to put any numbers at the bottom right corner. We can simply put down MgO. Okay? And magnesium oxide is white in color. Okay? Alright, so what about, I give you another example, maybe number 3. Potassium sulfide. Potassium sulfide. Now pay attention, now IDE, that means it is a monoatomic anion. Monoatomic anion. So sulfide, S2 minus. Potassium, K plus. So in this case, we need to have 2 potassium ions. So we will put down K2S. Okay, K2S. The color of it, if you're not sure about the color, white. Okay. Now let me try to do one translating from ionic formula to name. So here, FeBr2. So you know Fe is iron. Okay? And then Br is bromine. But pay attention, you don't put down bromine, you put down bromine. Okay? Now, also remember, for iron, it could be 2 plus, it could be 3 plus. So how can you tell whether it's 2 plus or 3 plus? Well, you need to first notice that Br is actually Br minus. Right? So, in this formula, we have 2 Br minus, right? 2 Br minus. So what does it tell you about the charge of the Fe ion? Well, in order to balance the charge, Fe must be 2 plus. Must be 2 plus. Okay? So therefore, this Fe is actually an iron 2 ion. Iron 2 ion. Okay? And color. So bromide doesn't carry a color, but iron 2 ion is having a pale green color. Okay? So this is how you deal with these questions. So again, pause the video, attempt all the questions yourself, and later on, check the answers. Okay? Now next page. Now we start talking about some covalent substance. Covalent substance. Now remember, at the beginning, I said that we have two types of compounds. We have ionic compounds and covalent compounds. Okay? Covalent compounds are formed when we have two nonmetals or more to form a compound, then they will form covalent compound. Now here, but you notice that I use the word substance because for covalent substance, it could be compound, it could simply be element. Now pay attention. We talk about compounds. We are talking about having two or more elements joined together. Okay? And the two elements must be different. Okay? So if I have hydrogen and oxygen react together to form water, then water is definitely a compound and it is a covalent compound because hydrogen and oxygen, they are non-metals. But if I have hydrogen and hydrogen joined together to form H2, then H2, do we consider it as a compound? No. H2 is simply an element, or we can say it is a molecule. Okay? We can't say it is a compound because it consists of one type of element only. Okay? So, therefore, in this part, I will put down covalent substance because this one could be covalent compounds. It can also be covalent molecules. Now remember, molecule stands for small particles made by one or more atoms joined together by covalent bond. Okay? So here, covalent substance involve atoms joined together by covalent bonds. Yeah? And many covalent substances are molecule. Okay? So molecules are small particles made up of one or more atoms joined together by covalent bonds. Okay? Now remember, covalent compounds, they are also covalent molecules. Okay? Because if you look at the definition, molecules are basically having one or more atoms joined together by covalent bond. It doesn't entail the fact that it must be two different atoms. Okay? So, just give you examples. If I have CO2, CO2, it is a covalent compound. It is also a molecule. Okay? No problem. But if I have O2, O2 is not a compound because only one type of atom. But it is molecule because it contains of one or more atoms joined together by covalent bond. Okay? And all of these are covalent substance. Okay? Is that clear? Is that clear? So make sure you understand those terms. What do you mean by molecules, compounds, covalent substance, something like that. Now, this table basically show you some common example of covalent substance. Could be compounds, could be elements. Okay? Just have a quick look, and perhaps it will be best if you can memorize them. Now, water, of course, is a liquid. It's a very good solvent. A lot of the things can be dissolved in water. Hydrogen is a gas insoluble in water, highly flammable. Okay. Oxygen, O2, right? It's a gas slightly soluble in water. It's oxidizing. Bear in mind, it is not flammable. Carbon dioxide, CO2, soluble in water. We can use saline water test to test for the presence of carbon dioxide. And carbon dioxide, when dissolved in water, gives you a slightly acidic solution. That's why our normal rainwater has a pH of 5.6 because of the carbon dioxide dissolving into rainwater, forming carbonic acid. Carbon monoxide with one oxygen fewer when compared to carbon dioxide, it is insoluble in water and it is also toxic. When we inhale carbon monoxide, it may cause dizziness. Methane is a gas that is insoluble in water and it is highly flammable. In our town gas, a lot of the component in our town gas is actually methane, but the major component in our town gas is actually hydrogen. Okay? Ammonia, NH3, is a gas that is very, very soluble in water. Okay? Ammonia has an irritating smell, and when it dissolves in water, they give you an alkaline solution. Okay? Sulfur dioxide is also very soluble in water, has a pungent smell. It also dissolves in water to give an acidic solution. Chlorine, also very soluble in water, and this one, it appears to be greenish yellow. Okay, greenish yellow in color. Okay, chlorine is toxic, so therefore it is used to kill germs in swimming pool. Okay, bromine, pay attention, it's a liquid. It's a dark red liquid. So it is soluble in water, but not very soluble. Very, very toxic. Okay, dark red liquid as element. When dissolved in water, they form brown solution. Bear in mind. Try to memorize these colors. Bromine dissolves in water to form brown solution. But if it dissolves in organic solvents such as oil, they actually give you an orange color. So try to memorize. Okay, bromine, orange in organic solvent, and then when it dissolves in water, it is brown. Okay, this color is frequently asked in exam. Okay, for iodine. Now iodine by itself, it is solid. It is soluble in water, but not much. It's a black solid by itself. When it is heated, it will sublime into purple iodine vapor. Okay. When dissolves in water, it will form a brown solution. So you notice that both bromine and iodine, when dissolved in water, give you brown solution. But when iodine is dissolved in organic solvents such as oil, they will actually give you a purple solution. Okay? So they exhibit different color in different physical states or when dissolved in different solvents. Okay? Now, chlorine gas, bromine liquid, iodine solid, right? Now here, basically, we mix water and oil. In this case, it is hexane. Okay, the organic solvent, the oil is called hexane. And obviously, oil, water, they are not miscible. So the oil should stay at the top, water stay at the bottom. And then the halogens, the chlorine, bromine, iodine, distribute themselves in the test tube. You notice that starting from the right-hand side here, this one is actually chlorine. So chlorine in water is colorless, but when chlorine dissolves in hexane, it appears greenish yellow. Okay? The middle one is actually bromine, because the bromine, well, when it dissolves in water, it gives you a brown solution, but when it dissolves in hexane, they give you what? They give you the orange solution. Okay? And the last one on the left, brown in aqueous solution in water, but purple in hexane. Okay? So you need to memorize these colors. Okay, next page. This one is also very important, writing chemical equations. So, in Form 3, we talk about word equation. For word equation, we simply know the name of the reactant the name of the product. Okay? But we have no idea about, first of all, the physical state. Simply looking at the name doesn't tell us the physical state. We don't know whether it's solid, liquid, gas, or dissolved in water. Secondly, we don't know the quantity. Okay? For example, you know that for photosynthesis, for instance, photosynthesis, carbon dioxide reacts with water to form glucose and oxygen. But how many carbon dioxide reacts with how many water to form how many glucose and how many oxygens? We have no idea from the word equation. Okay? So, here, in a chemical equation, we are able to tell the physical state, the quantitative relationship, basically how many reactants react to form how many products, and also the chemical nature, well, basically the chemical formula. Okay? Now, here, this is an example. This is when sodium reacts with water to give sodium hydroxide and hydrogen. And this is the chemical equation. Okay? Now, you notice that all the chemical species here at the back, at the bottom right corner, there is a bracket and showing you S, L, G, or maybe AQ. Okay? So these are the physical state. So sodium is a metal, is a solid, water is a liquid, gas, hydrogen is a gas, and aqueous, AQ, basically means sodium hydroxide has dissolved it in water. Okay? Now, we have also something you need to pay attention to. You notice that this equation has a number in front of some reagents. So those coefficient, those numbers, coefficient, basically describe the quantitative relationship. Okay? Basically, it means that 2 sodium reacts with 2 water to form 2 sodium hydroxide and 1 hydrogen. Okay? Why do we have to put down these numbers? Or in other words, how can we put down these numbers? Now, let me break it down to you. How does it work? Now, I do it at the bottom here. So let's just say I copy the equation down here. Okay? Now, let's just find out all the atoms on the reactant side and all the atoms on the product side. Now here, Na, so 1 Na atom. Here, H2O, so HHO, right? 2 hydrogen atoms, 1 oxygen atoms, right? On the right hand side, we have Na, we have O, we have H. And here we have HH. So these are all the atoms that we can find from reactant and product. Now you notice one thing. On the left hand side, we only have 2 hydrogen atoms. Well, on the right hand side, we have 3 hydrogen atoms. So this equation doesn't work because you may ask, where does this extra hydrogen come from? All the product, all the atoms of the product must come from the reactant. But just now, the reactant contains only 2 hydrogen atoms, but here product we have 3, so it doesn't add up. Remember, in chemistry, we have something called conservation of atoms. You can put it down, conservation of atom. That means, before you react and after you react, you should have the exact same number of atoms. The atoms simply rearranged. They simply rearrange themselves so that it gives rise to different products, different compounds. But at the end of the day, the number of atoms on both sides should be the same. You cannot create an atom out of nowhere. You cannot destroy an atom. Okay? So, how can we make sure the left-hand side and the right-hand side have the same number of atoms? Well, this is why we have to add these numbers. So just now I said that this reaction involving 2 sodium reacts with 2 water, right? So, in fact, we have 2 sodium react together. So if we put a 2 here, we have one more Na here. If we put a 2 here, we will have one more H2O here. Alright? So, and then when we put the 2 here, we have one more NaOH. Okay? Now, you can count the number of atoms on both sides. Sodium, 2 sodium each on both sides, so it's balanced. Hydrogen, 1, 2, 3, 4. 1, 2, 3, 4. So hydrogens are balanced. Oxygen, 1, 2, 1, 2. Again, balanced. Now here, this equation is said to be balanced because the number of atoms on both sides are the same. Okay? Now, you may ask, hey, sir, can I put down 4, 4, 4, 2? Atoms still balanced, right? Well, even though the atoms are balanced, but the 4, 4, 4, 2 is not the simplest one, so it is not acceptable. Okay? We want to have the simplest whole number coefficient at the front, okay, to represent the quantitative relationship. Okay? So that's the idea. You may also notice that the 1 here at the front is omitted, okay, because 1H2, the 1 is redundant. We don't add the 1 here, okay? If we have an unbalanced equation, we call it a skeleton equation, okay? Now, you also notice that we add this arrow, which is the same as the word equation, okay? This arrow must be properly written, okay? Should be like this. Do not give me something like this. Do not give me something like this, okay? It's not mathematics, okay? So this is how we write down a chemical equation, okay? Now, of course, I will give you some example. I will show you how exactly we write down a chemical equation in stepwise manner, okay? So let's have a look at the practice question. So you are asked to translate word equations into chemical equations, okay? Now, the first step, you must know how to translate English name into chemical formula. So that's why before I show you some common example of covalent substance, I also show you some common example of ionic substance. So hopefully you are able to translate the English into chemical formula. So first of all, carbon, C, is a solid. Okay? Oxygen. Now pay attention. Oxygen exists as O2. Exists as O2. Do not put down just O. Okay? Oxygen atom is highly unstable. Oxygen must exist in O2. Okay? And it forms carbon dioxide. CO2 is a gas. Okay? Now, at this moment, we want to look at the atomic composition. So, you see, we have 1 carbon, 2 oxygen on the left. On the right-hand side, 1 carbon, 2 oxygen. Right? So it is already balanced. It is already balanced, so we don't have to continue. Okay? And this is already balanced. Now, let's look at B here. So potassium is K. Potassium is a solid. Bromine, Br2. Again, bromine must be Br2, not just Br. And it is a liquid, if you remember. Bromine is a liquid. And they form potassium bromide, KBr, solid. Okay, KBr. Okay? Now, at this moment, we do something similar. We have 1 potassium atom on the left, 2 Br on the left as well. On the right-hand side, we only got 1 K, 1 Br. Okay? So, we want to balance the equation. Obviously, we are missing Br on the right. So, if we are missing Br on the right, perhaps we will add Br on the right. But can we simply add Br? Can we add a Br? No, because we don't have Br atom on the right-hand side. What we can do is to manipulate the number at the front. So here we can put down a 2 here. When we put down a 2 here, we have KBr. Okay? Now the Br are balanced, but the K is not. So what should we do? Of course, we put a 2 here. We get an extra K. Now, the atomic composition of both sides are balanced. So here, this is the chemical equation. Balanced. Physical state included. Okay? Now, so the rest of the question, again, do it by yourself, check the answers by yourself. Down here, you are simply asked to balance the equation. So you need to put the numbers at the front in order to make it balanced. Okay? Try to apply my method here. Okay? So the video stops here.